Hello everyone. Today I want to show you an example of using a Kalman filter to enhance the performance of a PID controlled multiple in multiple out model with simulated noisy sensors. First, let's have a look at our model. It's an aircraft in the longitudinal direction, and there are four variables to be controlled, including the axial speed U, the normal speed W, the pitch angle theta, and the pitch rate Q, which is the derivative of the theta. And we have two control inputs, being the elevator articulation angle eta and the engine thrust tau. So now let's have a look at our Simulink model here. And this part is our plant. And as you can see, the A, B, and C matrices we have derived here in the MATLAB code. And here are the PID gains for the two inputs. These are already tuned. We have set the reference values for the axial speed and the pitch angle for these to follow. For the axial speed, it starts as 180 meters per second, and at the 600 second it goes to 300 meters per second. As for this pitch angle, it goes from 0 to 0.2 radians at the first second. And we certainly will have some restrictions for the control inputs. For the elevator, it goes from negative pi over 4 to positive pi over 4 radians. For the engine, it goes from 0 newtons to 150,000 newtons. And we are going to simulate the sensor measurements of the aircraft. So this part is our simulated sensors. We have four sensors to be simulated, including the acceleration sensor, the pitch rate sensor, the axial speed sensor, and the pitch angle sensor. For the acceleration, is basically in the reality, it's an accelerometer in the aircraft. And the pitch rate sensor is usually a gyroscope. Both will have noise. For the other two sensors, it's the axial speed sensor, which is usually the manipulated results from the measurements coming from a pitot tube located outside the aircraft. And similarly for the pitch angle, it's usually manipulated from the angle of attack sensor located also on the outside of the aircraft. And they will also have noises. So the way we add noise to the sensors is like this. They are built-in Gaussian noise blocks in the Simulink. We set 0 mean and we give it a variance. And also for this one. So these are axial speed noise and the pitch angle noise. For the accelerometer and the pitch rate meter measurements, is a little bit more complicated because we need to first find the derivative of the axial speed and pitch angle in order to get axial acceleration and pitch rate. So I have written a script in this block here. It's basically the axial speed and the pitch angle at this state minus those at the last state, then divide by the sampling time. This is sampling time, 0.01 seconds. And certainly, we also add some noise to those measurements. You might wonder what are these noise values. So yeah, here. Now let's have a look into the Kalman filter part of the model. I know that Simulink has a built-in Kalman filter block, but I'm not using it because it's not straightforward to see what's happening inside the algorithms. Instead, I built a custom Kalman filter using the function block in Simulink, so that you can clearly see what's going on here. Now let's look at the inputs to the Kalman filter. So this Z and V are essentially these input ports coming from the sensors here. The Z is the noisy axial speed and the pitch angle measurements coming from the sensors. And the V it's the noisy acceleration and pitch rate measurements coming from another set of sensors, and they are fed time step by time step. These F, G, and H matrices are constant, which means they do not change per time step. And this F matrix, since it selects both the axial speed measurement and the pitch angle measurement, its identity. As for this G matrix, which applies to the V input, we need to multiply the acceleration and pitch rate by one time step to get the speed and the pitch angle. So we have sampling time times identity for G. And as for H, which selects output, it's also identity, since we want to select both the estimated axial speed and the estimated pitch angle. Now let's talk about the covariance matrices Q and R. So they are basically squares of the standard deviation of the error per one time step for each set of sensor. These are for the axial speed meter, and the pitch angle meter is straightforward, which is basically the square of the standard deviations in the sensor errors that will directly result in variance. As for this Q matrix here, since it represents the variance in axial speed and pitch angle computed from the accelerometer and the pitch rate meter introduced into one time step, we firstly need to multiply the errors in acceleration and pitch rate by one sampling time, which is 0.01 second, then square them all together to get the variances resulted in axial speed and pitch angle for each time step. Here, these are delays that keeps the P hat and the X hat values for one time step. This corresponds to here, where we will need the values of P hat and X hat from the last time step. Now let's have a look into the code. It's basically identical to what's shown here. Alright. Here we are simulating our model for 2000 seconds, and all the remaining are the codes for making the plots. So let's go. Yeah, as you can see, the axial speed sensor and the pitch angle sensor readings, being the green lines, they're quite noisy but have a relatively stable mean. On the contrary, the integrals of the accelerometer and the pitch rate meter have less fluctuation but are drifting heavily. The red lines are the outputs of the Kalman filter, and the black lines are the actual performances of the aircraft. I can zoom in here, you can see it more clearly. See how nicely the Kalman filter have fused the two types of measurements. And if you look at the black line, the aircraft's behavior is only very slightly affected by the noises in the sensors, and they are managing to track the reference values very well. You can also have a closer look at the parts when the reference is changing. Also nicely tracked. Finally, let's have a look at our actuator inputs. You can see the elevator angle is quite noisy, however it has never saturated, and we can kind of see that it reacts when there's a change in our reference values. As for the engine input, it's less noisy. It increased when we increased our reference pitch angle, and it also had a spike when we raised our reference speed.